parallel, and this is really has a big impact on software. We have hardware parallelism at all kinds of levels. We've got SSE instructions that do SIMD type computation. You've got simultaneous multi-threading. You've got multi-core. You've got small scale S&P. You've also of course got things like GPUs and stuff. So there's lots and lots of parallelism. More compute, more cores than people in the room, that sort of thing. It's also the case that I think that there are a lot of applications out there which have traditionally been written as sequential applications, which do in fact have parallelism in them. And this is sort of the place where these applications are going to have to start to be written or ported to run as parallel programs if they're going to continue to get an advantage from the future improvements in CPU technology. And this is really the big change, right? Is in the past, you could write a piece of software, Windows, Office, something like that, and every year Intel would make it faster for you. And you didn't have to do anything. You could just throw in more bloat, and Intel would come along and fix that for you because it would make it faster. And that's not going to happen anymore. If it's not a parallel program, it's not going to go faster. It's just going to sort of, get slower, probably. So this is our effort to try to address this. Of course, coming from a functional programming setting, and particularly, we're not trying to do high-performance computing. We're trying to look at more smaller scale kinds of parallel applications that do symbolic computing, and applications that might have parallelism at different granularities in the same thing. And lastly, I want to say a little bit about the design space. So historically, there have been people who've worked in the implicitly parallel space, like languages like id, ph, sisal. You have in the sort of middle, you have languages, I should probably have DPH up here, I apologize to the people in the back there. But Nestle, Nepal, OpenMP, these are languages where the programmer tells the compiler where parallelism would be good, but the runtime system, the compiler, actually figure out how parallelism, what to run in parallel, how to chunk things, etc. And then you can go sort of all the way to explicitly threaded programming languages like Erlang, Java, Concurrent ML, and of course concurrency extensions in other languages like Haskell, OCaml, etc., where you have explicit threads, explicit interaction between the threads, whether they're shared memory or whatnot. And Manticore actually sort of spans this both explicitly and implicitly threaded spectrum. So for the rest of the talk, I'm going to sort of cover three things. To start off, I'm just going to give an overview of what our language is, which is, hopefully will, give you a sense of what our approach to this problem. Talk about where we are, which is mostly about our implementation status, and then talk about some things that we're working on or planning to work on. So, excuse me. So when we started this project, we really wanted to make sure that we focused on parallelism and not on other distractions. So we were initially very conservative in our design. We took a subset of standard ML. So particularly, we very stripped down version of the module system. Key restriction is no mutation, although we do in fact have exceptions. So we're really looking sort of at pure, strict language here. And I think both strictness and purity are really crucial for building efficient parallel systems. And I think that this is a good spot to be in if you're trying to do parallelism. So that's our sort of sequential core, sequential base language. And then we have this implicitly threaded mechanisms on it, and I'll go through what those are in a couple slides. But these are the sort of fine-grained parallel programming things that we do. And then we also have explicitly threaded parallelism as well, which is useful for systems programming and for larger grained parallelism. But most of our research focus has really been on the implicitly threaded constructs. So we have several lightweight syntactic forms, and the idea really here is to take the existing sort of functional language syntax that we have for sequential programming and make minimal changes to it to support parallel programming. So we have parallel tuples. ML programmers are quite familiar with these, and we just add some syntax to that, and now they execute in parallel. We have parallel bindings, which are give you a kind of data flow like semantics. And I'm going to give some examples of these, so I'm going to skim through these pretty quickly. We have parallel arrays, which give us kind of a nested data parallel construct, and there have been several talks about this, both this morning and earlier in the week. And we have a parallel case construct, which gives you a kind of non-determinism for doing speculation. So ignoring parallel case, the other constructs actually all have a deterministic or sequential semantics. It's not quite just an erasure semantics, but in some cases, with tuples, it is. But once you throw case into the mix, then it's no longer deterministic. And the key thing to understand here is that these constructs are hints to the compiler and to the runtime. So they're a way of saying this is work that can be done in parallel, might be a good idea to do in parallel, but at the end of the day, the runtime system and the compiler really decide what to do in parallel and what to do sequentially. And you can do that both using static analysis techniques, which we've done some work on. Most of our work has been in the form of dynamic techniques for making those decisions. So parallel tuples are really easy. They give you fork join. So I'm going to use this very trivial example. We have a tree type with some integers at the leaves, and it's just binary trees, and a little example tree over here with 4 leaves. And this is a function that would add up the values of the leaves. And the idea here is at each node, it's telling the program tells the system that you can compute the 2 children in parallel, and that might be worthwhile to do. In practice, actually, you have to have very big trees before this becomes profitable. But you have trees of thousands or millions of nodes. It turns out to be efficient. And the way that gets decomposed, the colors here sort of show how that might get decomposed, where the blue, light blue thread is sort of the original thread, and then you have these other recursively created threads. And so on the right-hand side here is a kind of task dependency graph, if you will, which sort of represents what the dynamic computation would be like over that tree for that program. And that's, of course, assuming you have infinite resources, et cetera, or at least 4. So parallel bindings are a little bit more interesting. So this is just basically a modification of the traditional let syntax. So here we can bind B to the, in this case, to the right-hand side child of this tree, and we're going to do this multiplication. So we're going to say that B can be computed in parallel with computing A, and then we're going to check to see if A is 0, and if A is 0, we're just going to return 0, otherwise we're going to return A times B. So if A happens to be 0, then in fact we never need to compute A times B, and in particular, the subcomputation that's being done there might not be done or might be canceled during execution. So that's something the runtime system can do to reclaim resources. So a possible execution on our tree might look like this, where these circle lines through them represent cancellations, that at a certain point the blue thread recognizes that it has a 0, that 0 gets propagated up, and as it gets propagated up, the subcomputations on the other side are getting canceled. So that's a kind of a deterministic form of speculation, that it does speculation. It may be able to in some instances avoid computations, but it's still, the semantics of what happens is actually deterministic. Parallel case then gives us a non-deterministic approach. So this is a particularly silly program that looks for an element of the tree, a leaf. Just returns one of the leaves. And this is very much like join patterns. The idea here is that we run these 2 recursive calls in parallel, potentially, And question mark is a kind of a wild card that matches the value hasn't been computed yet, as well as matching any arbitrary value. Okay, so underscore is still the sort of strict, if you will, matching, but this is the kind of lazy matching, or ignore whether there's a value or not matching. So this will just either return the left, a value from the left or a value from the right. Yes?
Once you have a question mark, why do you need underscore? Why do you need both concepts?
Well, it might be the case that you really want to force the evaluation, but the underscore is still there, I think, just mainly to keep syntactic compatibility with regular pattern matching. Because you might have, I mean, you know, it's all, sorry, I have a better reason for why you need underscore. So these patterns can actually be more than just trivial patterns. Like here we just have variables, but they could be like constructors and things like that. And we're not decomposing the subcomputations of a particular column. We're only doing the parallel decomposition at the top of the column.
And the question mark can be only at the top level. Or
Right. So it's either a pattern is either a question mark or it's a regular pattern. So that's actually the right answer. So again, this is a possible execution where I think one is the value that got chosen, and so again we use cancellation in the implementation to prune off the subtrees that aren't. And I should say that there's a JFP paper on our website and that goes into all of this stuff in a lot more detail. So I will point you to that if you have questions. And lastly, we have the nested data parallelism. So this is, we actually provide an array comprehension syntax, more influenced by Nestle than by the more recent Haskell designs. In particular, we use the zip semantics rather than the Cartesian product semantics. I guess Haskell has both, depending on whether it's a comma or semicolon. Is that correct? Yeah. Okay. So I actually think that in retrospect it would probably be good for us to have both, but we haven't gotten around to that. But it does give you a very nice notation for writing this stuff down. In the most general form is actually a kind of partial map where you can have a predicate associated with the elements, and the pattern matching, by the way, also gives you another point where if that pattern is not is refutable, then there's another place where the matching could fail. But in this example, the patterns are trivial and there's no predicate, so just add two vectors or arrays together. And this is a slightly more interesting example. So this is actually a nested parallel example computing the Mandelbrot set. So in the innermost computation, we actually have a recursive function that is doing the core iteration, and then this is getting iterated over the grid. And so that's the a little bit more interesting. But you can of course do things that have an irregular structure and not just a regular structure. Okay, so the other concurrency mechanism we have is near and dear to my heart. It's my PhD thesis research, and this is perhaps an example that you never escape the PhD. But so we took concurrent ML and we've implemented these mechanisms, the concurrent ML mechanisms in Manticore and in PML, and this gives us explicit threading. It gives us preemptive scheduling. But what's different from concurrent ML and what goes on in PMLs is that these threads are actually can run parallel computations themselves. So a parallel thread could be doing something like a nested data parallel computation, and you could have multiple parallel threads doing that sort of thing. And so we have a lot of work to do there in terms of load balancing issues and whatnot, but we have actually some examples based on the ICFP programming contest a few years ago, the Mars rover, where we're actually doing some real-time, some parallel ray tracing in conjunction with parallel threads running, Martian AI and such other things like this. So it's a example of a kind of heterogeneous type of application where you have really parallelism going on in a lot of different granularities. So threads do not share state. Again, it's a pure language, although communication obviously is impure. But they communicate via message passing. Again, going back a long, long time ago, PLDI, that we use this idea of first-class synchronous operations or so-called events from concurrent ML as the mechanism to manage synchronization and particularly to manage abstraction over synchronization and communication. And the nice thing about that framework is it makes it very easy to incorporate other kinds of synchronous mechanisms, in particular interfaces to the system, like things like I/O, etc. So that's the language overview, and now I would like to talk a little bit about the implementation and where we are in terms of our set. So our approach to this project was to start from scratch. You know, we could have taken Milton, we could have taken Standard ML New Jersey or some other ML implementation and tried to make it work in parallel, and other people have followed that path. But our view was that it was much better to sort of start from a clean sheet of paper and really try to engineer everything from the very beginning to be parallel. And I think that has worked out fairly well for us in terms of things like scaling and whatnot. The downside of that, of course, is that we don't have as rich of an environment as, say, for example, the parallel Haskell people, because we don't have all of that sequential code that people have been writing for years and years, and we're now starting to try to address some of that. A big part of our research over the course of this project has been focused on developing really efficient work stealing techniques for managing parallelism, and there have been a number of papers and Mike Rainey's PhD dissertation that address these results. But this is really key to making fine-grained parallelism work effectively. One thing that we do that's a little bit different is we use ropes, which are essentially kind of trees where the leaves are sequences of unbounded size, maybe 128, 256. In our case, it's more often bigger than that. But it's a kind of a tree-like representation of an array. And one of the the reason for doing that is it's a much easier data structure to build up in parallel, because you can build up individual leaves and then you just concatenate them together. You're not doing a lot. You don't have to pre-allocate a big data structure to fill in, and you don't have to be doing a lot of copying, which is what you'd have to do if you were doing flat construct. Obviously, you pay some price on random access there. But the other nice thing about ropes is that that means that the work stealing actually works just sort of right off the bat for doing parallel decomposition for these things. And that's some of the stuff that we've been doing. So in particular, this upcoming JFP paper is about techniques for work stealing in that when you're computing over ropes or trees in general. We've also done some work on building parallel implementation of CML, and that was reported on a few years ago at ICFP. And lastly, and I'll talk a little about this stuff in a little bit more detail, one of the key things for implementing functional languages, of course, is garbage collection. And if you're doing it in parallel, you better get that right, because otherwise you have a huge sequential bottleneck in your program, and you'll never get scaling. So we put a lot of, and this is a place where the sort of clean sheet design really was crucial, because we were not depending on an existing runtime model, existing garbage collection architecture, or any of that. So we're really able to start from the very beginning and design a memory model that scales well, and then work with that, and work on the compiler and optimizations and whatnot to make that run fast. So that's a picture of what it looks like. It's a kind of combination of the Appel semi-generational collector, which was Standard ML used to use a long, long time ago. Standard ML in New Jersey, I should say, with the Delaunay, Leroy, Gantier parallel collector. And the basic idea is you have an invariant where pointers go from local heaps into global heap, but not the other way. And we have these virtual processors And every virtual processor has a chunk of the global heap that it can write into. And what this means is that we can do minor collections, which are by far the most common form of collection, completely asynchronously. So any processor at any time can collect its local heap without any kind of synchronization with any other processor. And likewise, major collections, which are when we start to promote stuff into the global heap, are almost completely asynchronous. It's only synchronization that comes up is when we have to grab a chunk of memory from the global heap. And then sometimes you have to collect the global heap in that collector. It's a stop the world collector, but it's also a parallel collector. And it does some clever things to try to preserve NUMA structure and whatnot. So with all the work that we've done, here's some performance curves. Ranging from things that are parallelizing quite well, like ray tracing. In fact, sometimes you get superlinear speedups for reasons that we believe have to do with the amount of cache available to the application, but we're not 100% sure about that. Black-Scholes, of course, is a very embarrassingly parallel computation. Quicksort we do fairly well on as well. Barnes-Hut, I think our issue here when we get out to 48 cores is that we just don't have enough parallelism. And that this is something we have to look into more. But that's the current state of the world. So where are we going? So I want to talk about a couple things. I'll try to talk about these quickly so I don't over time. So first of all, if you want to, this morning's talks in the Haskell workshop, or Haskell symposium, or ICFP talks from earlier in the week, that traditionally NDP is implemented by flattening, or sometimes it's called vectorization. And this is this transformation that takes the data and the nested data structures and flattens it out into flat representations with segment descriptors and also transforms the code. Now we don't do that. We basically just execute the nested structure of the program and we rely on our work stealing to make things run fast. And the observation, though, is that flattening does have some benefits. And on an SMP machine, it gives you better data access because you avoid levels of indirection. You may be able to unroll some address arithmetic and things like rectangular array access, that sort of thing. And if you have vector instructions, like most modern hardware does, you can also take advantage of those if you've done this kind of flattening. If you've taken arrays of pairs and turned them into pairs of arrays, etc. So we're looking at a new approach, which is to basically flatten data, but not flatten code. And this is sort of, it was Adam Charlotte's dissertation research, and we're in the process of sort of making it more industrial strength. We do have some preliminary results. So here are a couple examples. So Mandelbrot on the, which essentially is that program that I showed you before, except running at a larger scale. For something like that, we get some benefit from the data access, but not huge. For an irregular program like a sparse matrix, sorry, that should have been SMV. Anyway, sparse matrix times vector multiplication, we actually get substantial speedups. In fact, better than it looks like better than linear speedups, but that better than linear is coming from the fact that the baseline doesn't take advantage of certain monomorphization optimizations that we can take advantage of because we've done flattening of the data structures. So that's one of the other big ones. So I'm running out of time, so I'll have to go through this one quickly. So another thing we're working on is shared state. And really the motivation for this, so we started pure, and now we're going to dirty ourselves a little bit with the mutability. And the idea here is because there are certain kinds of applications where shared state will give you asymptotic performance benefits, and you just can't win those back with parallelism. And so transposition tables in search is one example. There are also kinds of applications like mesh refinement where running parallel computations over shared data structure is a much more natural way to program it than trying to figure out a way to make the structure partitioned and re-merged, etc. And the observation, I think, which motivates this is that mutable shared memory is a hardware-accelerated broadcast mechanism. It's a really powerful mechanism. It can kill you. I mean, this is, you know, it can, and if you abuse it, it will kill your performance. But if you take advantage of it, you can get tremendous benefits. And so that's our goal. So quickly, I'm almost done now. So we have low-hanging fruit, which is memoization. We have things that are a little bit more difficult, but we think we can do with a kind of inference-based, analysis-based introduction of essentially SPM-like mechanisms. And in the long run, we want to think about high-contention data structures like shared work lists that come up in some algorithms. I will skip this slide because I think I'm going to be out of time. But there's a bunch of things that we're doing to try to make the compiler better, and in particular to try to make the compiler more robust and more useful to people outside of our group. Because right now it's really you have to be, you know, there may be 10 people in the world, if that many, who can really make Manticore programs work well. So to conclude, I really think that strict pure FP is the place to be if you want to do parallel computing. I think that state is evil. I think people may have heard me say this before, but I will say it again. State is evil, but it is necessary. And so we have to just figure out how to manage the evil. And I think it's really better to try to build for parallelism from the start. I mean, there are costs to doing it, but I think at the end of the day, where you end up is going to be a much better story with respect to parallelism, and the future is parallel, it's not sequential. So, you know, you might as well abandon our sequential code bases early and get ahead of the train rather than get run over by it. So, questions?